Okay, with a little bit of delay, I think we are ready to get started. So the first talk will be by Lili Tong on non-malleable reductions of knowledge. And let's see. Do we have a clicker?
Oh, the clicker. Oh, there. Yeah, there. Okay.
Okay, so feel free to go with it, Lili.
Sorry, this is not my slide.
Non è questo.
It's non-malleable. Lili.
Can you see? We got it on the program. This one? Okay. It's ready. Okay. Ready.
Okay. Good afternoon. My name is Lili. I'm a PhD student at Eurocom. And today I'll be presenting this work with my advisor Antonio on non-malleable reductions of knowledge. So in this talk, it will be split into three parts. Firstly, we'll do a bit of recap on the background. And then we propose some concrete conditions we can put on reductions of knowledge to make the composition non-malleable. And at the end, we take the lattice-based proof system Labrador as a application. So the first thing we recall is a proof of knowledge. In a proof of knowledge, there is a prover and verifier, and they share some common instance X, where the prover have, in addition, a piece of witness W. And using this witness, the prover can generate a proof, send it to the verifier, and the verifier decides if she's going to accept or reject the proof. And one security property that is required to be satisfied by proof of knowledge is knowledge soundness, where intuitively it means that there exists an extractor algorithm that can extract the witness from the prover. And there's another property we're interested in is zero knowledge, which means that there exists a simulator algorithm that, given as input the instance, it can simulate the proof. Then we move to reduction of knowledge, which is formalized in KB22. And in some sense, a reduction of knowledge is a special kind of proof of knowledge, where for the prover, at the end of the interaction, so after it outputs the proof, it can output a target witness that lies, and together with a target instance that lies in some target relation. And moreover, there exists a public function that, given as inputs the source instance X and the proof pi, can compute the target instance X prime. So as a first example, we can look at Schnorr, which is a proof system for proving opening commitment relation. So we see that in view of a reduction of knowledge, Schnorr is a reduction with the source relation and target relation to be coinciding. And the target witness is of the form piece of randomness sampled by the prover plus AW, where A is a uniform challenge from the verifier. Now, reduction of knowledge is deeply connected to a proof of knowledge in the sense that we can associate to each reduction of knowledge proof of knowledge by defining the proof of knowledge verifier to, in addition of running the verification check on the proof, it's gonna run a target relation check on the pair of target instance and target witness. And using this association, suppose we have some security property defined on a proof of knowledge, we can import it on the reduction of knowledge by requiring its associated proof of knowledge to satisfy that security property. So for instance, when we say a reduction of knowledge satisfies zero knowledge, it means that exists a simulator that can simulate both the proof pi and the piece of target witness pi w prime. Now, on a high level, a reduction of knowledge can be seen as an arrow between two relations. So it starts from the source relation and lands in the target relation. And as arrows, they are naturally composable in a sequential way. So concretely, given two reductions of knowledge with coinciding the intermediate relation R2, we can define the composed reduction by, for the prover, we first run the first prover and pass its returned piece of target witness to the second prover and later complete the proof. For the verifier, it's essentially the sequential check on the two proofs, pi 1 and pi 2. Now, nowadays, reduction of knowledge is already a popular tool to construct proof system. For instance, say we have a proof system for relation R, and we want a proof system for, say, relation R1CS, then we just need a reduction going from R1CS to that relation R that proof system is proving. And in addition, we can have the kind of folding schemes such as bulletproof, compressed sigma protocol, lattice fold, and Labrador, etc. And another pro is that for a proof of knowledge that is constructed in such a way, in the sense that it's a sequence of composition, it's a sequence of reductions of knowledge, then oftenly each reduction is quite simple in the sense that it consists of only 2-3 messages. So analyzing if this kind of small reduction satisfies some proof security property is usually quite easy. So for instance, in KP22, they analyzed that for two reductions of knowledge, if they satisfy knowledge soundness, then the composition will remain to be knowledge sound. So the goal of this work is to analyze the security property of some complicated proof of knowledge through the lens of reduction of knowledge. And here we take this security property to be non-malleability. So what's the motivation to look at non-malleability? This is because in practice, knowledge soundness itself is often not enough, in the sense that imagine a scenario of a blockchain where the adversary might have, in its view, some history proofs, and we wouldn't like it if it has the ability to forge another proof without a piece of witness. And this is captured by non-malleability. And in case of the exist a zero-knowledge simulator, this is approximately equivalent to simulation structurability, where the adversary would have oracle access to the simulator, so it can make some simulation queries on some instances. And at the end, it would need to output a forged proof with respect to some instance. And for such adversary, we would require the existence of an extractor to extract a piece of witness from it. So that's simulation structurability for a proof of knowledge. And as we've described before, how using the association between reduction of knowledge and the proof of knowledge, we can define what is meant by simulation structurability for a reduction of knowledge, where it's almost the same thing, except that for a reduction of knowledge, its associated proof of knowledge would output the proof that consists of the proof for the reduction and the piece of target witness W prime. So the adversary would need to forge also this kind of complete proof that includes the target witness in it as well. And as a result, we propose this framework for non-malleable composition of reductions of knowledge. And then we take the lattice-based proof system Labrador as an example. And since Labrador is not zero knowledge, we construct a zero knowledge layer for it that is small in proof size, so that the composition of the two wouldn't ruin the nice property that Labrador has compact proof size. And at the end, we prove simulation instructability of zero-knowledge Labrador. So if we recall in the game of simulation instructability, we need a zero-knowledge simulator. So the first question is, how can we obtain zero knowledge on the composition of two reductions of knowledge? Well, canonically, there are two cases. Firstly, suppose the first reduction is zero knowledge, meaning that it exists a simulator that, given as input the instance, it can simulate the proof and the piece of target witness W prime. And in this case, we can pass this simulated target witness to the second prover to let it complete the simulation. And the result is, in this case, if we require the first reduction of knowledge to be simulation instructable, and the second reduction to be satisfy this property called unique proof, meaning that for each instance X, its Fiat-Shamik proof will be unique. Then with these two properties, the sequential composition of the two reductions of knowledge would remain to be simulation instructable. Now, suppose in the case that the first reduction is not fully zero knowledge. However, there exists a partial simulator that's given as input the source instance X. It can simulate only the proof, but not the piece of target witness. In this case, we see that if we let the second reduction to satisfy zero knowledge, then we can pass this simulated target instance to the second simulator to let it complete the simulation. So just to compare the two, we see that in the second case, there is no simulated target witness, but there exists a simulator for the second reduction that can take as input this simulated target instance to complete the simulation. Now, in this case, we notice that if the first reduction satisfies this property, what we call as sim-mexed for partial zero knowledge, then and the second reduction satisfies sim-mexed, then the composition would remain to be sim-mexed. And we elaborate what does it mean by simulation instructability for partial zero knowledge now. On a high level, it's an analogy of the simulation instructable game, but the simulator now is only a partial simulator. So the other three can still have overall access to this partial simulator. So make some simulation query on instance X, and in its view, it would only have access to some simulated proofs without the part of the target witness. However, we require it to output the forgery that contains both a forged proof and the forged target witness. So the question now is, how can we prove simulation instructability for partial zero knowledge? And to do this, we first look at how can we prove simulation instructability. And there exists a line of work that sort of relates simulation instructability to some uniqueness property. And in particular, in DAO Group 23, they proposed that if a proof system satisfies K zero knowledge and K unique response, then it satisfies simulation instructable. And here, for partial zero knowledge case, we have this analogy of if it satisfies K partial zero knowledge and K hard to invert, then this reduction will satisfy simulation instructability for partial zero knowledge, where by K zero knowledge, it means that the simulator would only reprogram the random oracle on the kth round. And by K partial knowledge, it's essentially the same thing, but the object transfers from a full simulator to a partial simulator. So let's compare a bit the unique response property and how to invert property. And in DAO Group 23, they define the K unique response game as follows. So the adversary would only have access to the random oracle, and at the end, it would need to output for the instance X a challenge C and two pairs of proofs that are distinct, but they have a common K prefix. So mean that it's diverting on the tail. And this security notion was later weakened to a weak unique response game in GOP23, where the adversary would have access to a simulator, so it can make one simulation query on some instance X. And using this simulated proof, it would need to output a forged proof pipe star and a forged target witness W prime, where there needs to be distinct proofs, because otherwise you can use copy and paste. But they need to have a common prefix. And now for the hard to invert game, essentially it's an analogy of the weak unit response game where we swap the simulator to a partial simulator. So the adversary would have all access to it, would have access to one simulation query. So it makes a simulation query on X, and since it's a partial simulator, it can only return just the proof without the piece of target witness. But this adversary would need to output a proof pi star and W star. And one difference is that we only require the forged pi star to share a common prefix with the simulation pi. But yes, but we don't. It's okay that pi star would equal to pi, because the adversary will need to output this extra little piece of target witness W prime. So as a little summary for the case 2, we have that if the first reduction satisfies K partial zero knowledge and K hard to invert, and the second reduction satisfies Simex, then the composition would be Simex. Now, as an application, we look at Labrador. So Labrador is a proof system for the relation R, where on a high level it's a function satisfiability over cyclotomic ring, and for the functions defined for the function of the form to be the sum of quadratic parts and a affine part, and moreover, this witness has a norm-bound beta. And the motivation to look at Labrador is that it's a recursive proof system, in the sense that in view of reduction of knowledge, its source relation equal to its target relation, but it's the rank of the target relation is shrinking. So we can apply this the main protocol of Labrador recursively to reach a compact proof size. And another reason is that Labrador is built in a modular way, in the sense that we can further decompose Labrador to be the composition of 3 smaller reductions. So it's firstly doing a norm check, and then doing the aggregation, and then at the end doing the amortization. And one thing we observed is that with a slight twist on the relation, we can argue that Labrador satisfies, a unique proof property. So now we need a zero-knowledge layer for Labrador. And on a high level, we obtain this the zero-knowledge overall by the paradigm of ZK plus prover. So we design a full zero-knowledge layer for it, and then as we run the prover of Labrador on the simulated witness, we can obtain zero knowledge on the composition. For the zero-knowledge layer, the masking process is done in 2 steps. Firstly, we perform a nova-ish reduction. That is, essentially, it's sampling a randomness Z, and then it commits to the cross terms. And for the source witness S after masking, is of the form Z plus alpha S, where alpha is a challenge element, and zero knowledge on this element V is obtained via rejection sampling. Now, one thing we notice is that the first step, pi nonlinear, is introducing some new variables W due to the cross terms, and however, they satisfy some affine relation. Therefore, in the second step, we use a classical sigma protocol for affine function satisfiability to further mask the variable w. And as before, after masking, it's of the form z plus alpha w, where z is a randomness and alpha is a challenge element. And zero knowledge on this element is obtained by rejection sampling. So one thing we notice is that this way of obtaining zero knowledge, it doesn't really fall into the two paradigms we've introduced before, in a sense that for the second reduction pi linear, the simulator can only be a zero knowledge simulator if it has as input a part of the witness v, and without it, it cannot be fully zero knowledge. For this part of witness v is simulated by the first simulator of pi nonlinear, and therefore we notice that this problem can be solved by defining a so-called extended relation, where essentially it's a syntactic change where we move the part of the witness v to be part of the instance, and leaving the witness to be only the w. And we can define naturally to extended relation, to extended reduction, where for pi nonlinear, it's the extended one would have a target relation to be the extended R, which is the tilde R. And for the linear, it would have source relation to be the extended R. And we notice that with this slight syntactical change, we can reduce back to the partial zero knowledge plus zero knowledge case. However, so using the case 2 that we introduced before, if we can argue that this extended pi nonlinear satisfies Cmax for pzk, and the extended pi linear satisfies zk, satisfies Cmax for zk, then the composition of the two extended reduction would satisfy Cmax. But the problem is, what we're interested in is the composition of two original reductions. So it's the composition of pi nonlinear and pi linear. But what can we say about the simulation instructability of this? And this motivates the last case of the framework, which goes like, if there exists an extended relation for the intermediate relation, that the extended pi 1 satisfies partial zero knowledge, and the extended pi 2 satisfies zero knowledge, then if the first extended rock satisfies Cmax for partial zero knowledge, and the second extended rock satisfies Cmax, then the original would be simulation instructable. Now, just to put everything together, we analyzed that the first step in the ZK layer, the pi nonlinear, the extended version satisfies Cmax for partial zero knowledge, and the extended pi linear satisfies Cmax. And therefore, by the case 2 we introduced before, is the zero knowledge layer will satisfy Cmax. And again, since we analyzed at the beginning that Labrador satisfies unique proof property, and using the fact that ZK layer is Cmax, we conclude that the zero knowledge version of Labrador satisfies simulation instructability. And that's conclude this talk.
Thank you, Lili. Let's see, Alberto, you may go here already to set up so we can run smoothly. And meanwhile, if we have any questions, then please ask them.
So, as far as I understand, you end up with a commutative square with the two reductions. So instead of going upward, you go downwards, right? But is it really a commutative square, or do you need some constrictions or some
Sorry, I didn't get what you mean by going up and going down.
Oh, sorry. So I am just thinking about, reduction of knowledge as errors, as you were mentioning in the very beginning.
Yep.
And so as far as understanding is, instead of going through the usual reduction, you define two other arrows.
I mean, a sequential composition of two reductions.
Exactly. So do you have some hypotheses for these compositions, or it's really a community square?
Oh, it's a general construction.
It's
a general construction.
Okay, perfect. Thanks.
Any other questions? Okay, let's thank Lili again.